In this video, we are going to look at two different types of rate information that you can get when you're running a reaction and talk about what that type of information means. We'll also look at some other data in the next video, but one of the common things that specifically relates to the definition of rate that you will get out of these either graphs or data tables. We're going to do ours with a graph for this video. One of them is the average rate, and so this is just the rate over a range of time. And from a graph like this, you can get that information if you just have two data points. So over a very specific period of time, so I don't have any numbers on my time scale here, but this is a time scale in microseconds. And so let's say I want to know from this time point to this time point about my rate of reaction. I have a choice, right? I've got a blue line showing me how my reactants disappear. I've got this green line showing me how my products appear. I can define the rate of reaction in terms of any of them. So whatever I do, as long as I'm following those conventions from the previous video, I'll be able to calculate that value appropriately. So let's do it for, say, O2, which is one of our reactants that's disappearing. So it's on the blue line. So at the first time point, this is my O2 concentration, and at the second time point, this is my O2 concentration. So if I make a little triangle here, that might look familiar to you because it's how you calculate the slope of a line. This, rise over run part, the rise part, the change in my y component, this is delta, concentration of O2, and this change in my x component is delta T. Now, I'll need to use the reaction to get the appropriate definition of the rate in order to get the correct value for the average rate over that time period. But this is how I can pull that information out of the graph. The other information that you can get off of a graph like this is the instantaneous rate, so the rate at a very specific moment. And so in order to do this, we're looking at exactly one point in time. So there's no delta T, technically, right? The point that we're looking at, say I want to know at exactly this point on my NO line what the rate at that instant is. The only way that I can pull information out of this is if I say, do something like a tangent line. So if you take a tangent line and please forgive me for my line not being so perfectly a tangent, but this tangent line, if I find the slope of that line, it will give me the rate at that very instant. So let's do an example that shows how we use some of this information in problem solving. I'm going to pause, get it written down, and be right back. So our example problem says in the first 10 seconds of a reaction, the I- concentration dropped from 1 molar to 0.868 molar. Calculate the average rate of reaction in these 10 seconds, and then we have the balanced equation. So the information that we're given in the problem, we are given an initial and final concentration for the I-, and then we're given a time point, but since it's in the first 10 seconds, the 10 seconds is T2, but T1 was 0, so 10 seconds is our delta T. So in order to get the rate, we need the definition of the rate of the reaction in relation to the I minus, and then we have everything else that we need to plug in. So I minus is one of our reactants, so my rate definition will have a negative in it. It has a coefficient of 3, so it'll be negative 1 over 3. And then delta concentration of I over delta T. And just to explicitly have this out here, now you probably don't need it, but just in case, we're talking about negative 1/3 times concentration of I minus at T2 minus concentration of I minus at T1, T2 minus T1. So negative 1/3. My concentration of I minus at T2 was 0.868 molar minus 1.00 molar divided by 10 seconds minus 0 seconds. So if I punch all of this into my calculator, the value that I get is 4.40 times 10 to the minus 3rd molarity per second. So we have even a unit that reminds you of that speed unit that we were looking at in the first video. So we had kilometers per second. Now we have molarity per second. So the rate of the reaction is proceeding on average in these first 10 seconds at 4.40 times 10 to the minus 3rd molarity per second. So I want to add a second part to this problem because I think we should look at the wording because you will see problems like this, and I think the wording is a little bit awkward, so I'll point out the part that will always show up that helps you do the right thing for the problem. So the second part, I didn't label the first part with an A, but I am going to label this with a B, and I don't know, we'll just deal with it and survive. So the second part says, what is the rate of change in concentration of H plus during the 10-second interval? So it's not asking just about the rate of the reaction because we already calculated that. So regardless of how you define it, the rate of the reaction is the number that we calculated in part A. But when it asks you for the rate of change in concentration, it's asking you for delta H plus over delta T. So just that part that doesn't include the coefficient that we have to put in there, and it doesn't include a plus sign or a minus sign, depending on whether it is a product or a reactant. So the first thing to do here is to write the definition of rate in relation to the H plus. So it is a reactant, so it gets a negative. It has a coefficient of 2, so it gets the 1 over 2, then delta H plus over delta T. So now this is the thing that we're solving for, and the rate of reaction, like I said, is the same numerical value from earlier. So the things that we know that we can plug in, the rate value is 4.40 times 10 to the minus 3rd molarity per second. And now this is equal to negative 1/2 delta concentration of H plus over delta T. So to solve for delta H plus over delta T, I just multiplied both sides by a negative 2. And my delta H plus over delta T, that's equal to negative 8.80 times 10 to the minus third molarity per second. So you can report how an individual component is changing with a negative sign. So in this case, that negative is reminding us that this is a reactant. So the concentration of H plus, it is changing in a negative way because it was a reactant. But if I then took this number and used it to calculate the rate of the reaction based on the definition, I would get a positive value for the overall rate of the reaction.